Yeah, so I know this is the last call before the lunch, so I will make it quick. But basically, that I will try to actually summarize a lot of the things that we have been discussing this morning. Is that the trend where we are seeing more proof systems that are application specific. So when I work on software and hardware in ZK, especially when I work on hardware accelerator, a lot of the investors are asking me this. Are you expecting that there is something like a new growth system where everyone just use that proof system and nothing else? And nowadays, I think the conclusion is very simple, is that is very unlikely going to be the case because we see that the proof systems are going to be very diversified. And in today's talk, I will talk about several aspects of it. That we see application-specific curves being used in our system. We see application-specific gates. And now we also see application-specific hardware acceleration. And so I will start with curves. Many of you have already been using elliptic curve in our proof system, like BM254, BLS12, 3 and 1. But in the recent year, you start to see some of the curves that are not designed to be for general purpose. They are designed for some specific application. And using this curve, the application becomes super efficient. And let me give you probably the first example is ZC. ALIO use these to provide function privacy for computation. And what they do is that they pick a specific curve where they can easily construct recursive verification. And in the past year, you also see more examples. They are now have even more application. You have customized curve that allow Zcash to be running over ED25519 signature, which remove the need of using drop curve for signature. And you are able to compatible with Cardano, Solana, and algorithm address. And you also see example of cross-chain communication that using a different curve, you can make signature verification in this ZK bridge very efficient. And you also see from Chen that they design a specific curve that are able to do time lock encryption very efficiently. And recently, there is also from HashiCloud, they design, they found a curve that is actually very efficient in proving proofs in subnet, basically verifying start proof. This will be very useful in compressing down the size of the start proofs. And in this call, I will also talk about a new one, basically that how do you do Zcash over the 0x address? Zcash always have their own address. Can we just use the same address as every other things? And I will talk a little bit about several examples in here. So this is a work from HashiCloud. They want to find a curve that is able to do computation that verify the start proof very efficiently. And what they do is that they observe the start field. It actually have very good FFT space. And what they do is that they just simply find a curve where the scalar field is exactly the start field. They are able to create one, and this will be useful to verify start proof. That code is already open source. And the main benefit from this is that usually when we try to, when a limitation is that usually you will have to do non-native computation when you verify something. This might cause a 1,000 times slowdown. But if you are able to use a customized curve, you may just remove this overhead immediately. And now I will go to another example, which is a different situation. The previous one is a pairing-friendly curve. And we also have curves that are working on the case when it's not pairing-friendly. And this is what we do in order to create zero cache over ED25519. The problem when we encounter here, there are two things. Firstly is that ED255 is the field doesn't have a very good FFT space. That means that running gross16 pronged over this field will be very difficult. And especially, the reason why it doesn't have FFT space have to do with the factorization of the P-1. It doesn't have some easy way to combine the number together. So, but you can still construct a curve that is non-pairing friendly, and it can build the Zcash with ED25519, and it can avoid the problem of FFT space by using bulletproof. And so I will just talk about basically this have been used in production. That is that you can use this specific curve with bulletproof, and that you can let it work together with traditional Zcash proof over BLS12 3.1. And you can build zero cache over ED25519 address. It means that you can build probably I would say a ZK rollup over algorithm, Cardano, or so on that use exactly the same address format. Okay, and today I will talk about like some newer techniques that we show up here. Is that like even if you find you are working on a curve where there is no FFT space at all, you can also do gross 16 and plonk over that. This is something that people usually believe to be impossible. And the idea is that like the idea is that we want to really have zero cache also for 0x address. The problem is that like although bulletproof work very nicely, we already have that in production. Bulletproof have long verification time, long proving time. And so we are thinking whether or not we can just use plonk or gross 16 because they have fast proving, fast verification. And so if the circuit is very small, in our case, verifying a signature, then what you can do is actually to try to find a way to bypass all the FFT limitation. And so here I basically just go a very high level is that like, so what you do is that you replace all the tools in gross 16 and plonk that require FFT with things that don't require it. And you replace FFT with like interpolation. You don't use FFT to multiply to polynomial. You also try to use a vanishing polynomial that is now very different. And you also change how permutation in plonk work. And so I will just go over a little bit detail, but basically that this gives you some benefit in like reducing the amount of the like operation that you need to do when working over a very difficult like FFT space. So I think I will just run over these slides. But this gives you something, is that previously when we are dealing with curve where the scalar field have no good FFT space, we have to go to things like bulletproof or Gemini because they don't require FFT. And now I want to show that like, actually it's practical to also develop gross 16 and like plonk over this curve that doesn't have good FFT space. And so this kind of just like lead to basically this like now the new universe of the application-specific curve. In some situation, you build application that need to verify certain like crypto operation over some curve. What you can do, you find good curves that are designed for that. They can be pairing friendly, they can be non-pairing friendly. And you can also try different types of the tool for that. Actually, a lot of the curve here work for the non-pairing friendly case. Okay, so the second thing, and probably this will be related to Daniel talked about ML, and I will also talk a little bit about why it has something to do with like a lot of the protocol that we have been seeing today. That is, you are creating proof system where like the customized gate are application specific. We previously see a lot of the proof system already there, gross 16, Marlin, and plonk, and you may have the question that why suddenly stop? Why suddenly so what happens is because that now every company seems to have their own proving system. This afternoon, you will hear about Plonky 3. And so, but the reason for that is because that every company now have their own need for their proving system. So a lot of the company are already doing this, is that they want to do snap-friendly hash function. What they do, they create a customized gate for that. This brings down the cost by probably, in the ideal case, 20 times for hash function. And there are also a lot of the computation where it involves ring checking. You build a customized gate like that, 3 times speed up immediately. So basically, that customized gate is magical in that it brings you speed up immediately. And so, and probably the most like amazing example is that if you are building application, if you are building a customized gate for some specific snap like function, and this you can see this is a very complicated customized gate. This will allow you to reduce the overhead from that very good optimization implementation of rescue by another 90 times, making Merkle trade in ZK Snap very efficient. So this is basically another example. This is that this basically how many speed up it brings over R1CS, 1,000 times of the speed up. So basically, this is another example. Customized gates bring you speed up of 100 to 1,000 times. And you don't need to use any hardware acceleration for that. And this, you can see why so many companies are exploring customized gate. This is kind of free product that you just adding a few customized gate, everything becomes faster. And the way that we kind of design this is actually not that difficult. You observe the algorithm and you build customized gate that looks almost like that. And the reason why customized gate work have some theoretical reason, because by using customized gate, you increase some overhead, you reduce some overhead. Eventually, usually, what you do is that you make the witness sparse, you reduce like the length of some like non-sparse polynomial, And that you also, how to say that, like this is an optimization problem that in the end, we often see very good result in using customized gate. And I think a good example is that I know Scroll have been using customized gate, 3,000 customized gate, if I remember the number correctly. So this is an example that now you can see if someone is using 3,000 like customized gate, you are not going to expect a new growth system. And I want to say that the lesson here also go to hardware acceleration. So hardware acceleration is a very popular topic today, and that we have been thinking about what would be the good model or good abstraction for hardware acceleration. And many people will be thinking about this graph. That is that we have basic computation like MSM, FFT. We are thinking about that in a general mindset is that if we are doing growth system, we optimize these two, everything gets speed up. But the problem with this is that it have a very high communication overhead. And let me show you some number. This is from NVIDIA GPU, very good one. I am using Coreway's like cloud server. I do FFT and MSM using NVIDIA GPU. This is already several times faster than CPU. And one thing you can see is that communication in both cases are the dominating overhead. And that restriction have a lot of reasons. PCIe is not fast enough. But this is an important signal to tell you that the model that we have here might be a little bit too simple because it provides no opportunity to reduce the communication overhead. And so from this example, and also this actually is being reflected in the Z-Prize competition, if you have heard about that. In that competition, it asks contestants to develop proof systems that are very efficient, like basically make hardware acceleration that are very efficient. And they have to roll out communication overhead just to make sure that the competition will be meaningful. Because otherwise, it becomes communication optimization. And we see the reason is because that if we are using GPU and so on, communication is going to be really the major problem. And we are not expecting that to go better very soon. And this is also not a surprise. MIT have a paper that actually asks this very intriguing question. Does FHE need compute acceleration? And you probably will worry that the answer is no. The answer is yes, but they actually added a condition. Is that you need to firstly address memory bottleneck first, because they also observe that in a lot of the FHE chips, all they do, basically all the speed up come from reducing communication overhead. And this is actually kind of like give us another lesson is that in order to really develop like good hardware acceleration for ZK, you need to really think about like all these costs, not just computation, you also need to think about communication. And here is a model that made a better sense. You provide a richer API, you allow some data to be sent into the chip and let the chip remember them so that you don't need to send them again. This is level one. And if you accept this one, this is basically stage one of modern hardware acceleration for ZKP. This is just the beginning. Because another thing that we talk about a lot is actually that like the chip is just receiving a lot of redundant information. And I can kind of just give an example. If you think about proof system that we are using today, like in Zcash, you actually are only having a very little secret information that you really need to prove. But the proof system involves polynomial that are so large. And in Daniel's case, actually have already shown is that maybe the secret information is just the image. But the amount of the data is so large that the memory it doesn't even fit into that. And this is basically the problem. When we have a very small secret, when you are doing the proof generation, you convert them into a huge amount of the polynomial that you might be actually sending to the GPU. Why not just send the actual secret? That's the first thing. And something that is even worse about the wasteless, and probably is specifically in the case of machine learning, is that the model is actually not that complicated. Also, in a lot of the proof system, you have a lot of the recursion. For example, this is a Merkle tree. You do that layer by layer. You can write the Rust code very easily, but the circuit after the compilation also become a bunch of the polynomial. And this polynomial would need to be sent to the GPU in order for the GPU to do the computation. So the question here, why not just let the GPU or your accelerator to know this description and figure out those polynomials themselves? And this kind of lead to what I believe would be like basically the correct way to abstract and model hardware acceleration for ZK. You need to have devices to receive minimal information that is really necessary. and you send application-specific code, which might including a decompression algorithm to ask to tell the GPU or ASIC how to really expand those data into polynomial and other things. And I think one fact about that is that like, you actually already see this type of the implementation in the real world. And the best example is probably ALEO mining. ALEO miner have already tried a lot of the effort in not sending too much information in the GPU and try to send more useful information to the GPU. And I previously, one of my clients is actually like a ALEO miner. They are in Singapore. They have better FPGA implementation than ours. I asked them why. They tell me a simple thing. They do that for a living, and therefore they are good at that. And this is probably a lesson is that like, so application-specific approach for hardware acceleration will work because you can see that people who do that for a living already use that in their like business, mining. And that is basically all I will be talking about the cloud. I think I covered several different aspects, but the main idea is very simple, is that you are not going to expect a single proof system that will be used, like basically that is not going to be a single curve, single proving system. It's going to be very diversified. And also, you need to really learn about this like that diversified approach in designing protocol. And next week, I will actually have a talk about one of the hash functions that I just mentioned, how to design customized gates for very efficient Merkle tree next week. And you can find that from Daladin's reading group. And I believe this is now is the lunchtime.